This worksheet is about kinetic energy and power, obviously, because that's the title. Kinetic energy is another kind of energy because it has the capacity to do work. It is the energy of motion. Moving objects can do work. A bowling ball rolling down an aisle can do work on the pins when it hits the pins at the end of the alley. Things with motion can do work. Um, how do you find out how much kinetic energy an object has? By definition, it's the work to stop. It's whatever work it would take to stop the object or get the object from rest to a certain speed. Just to make this something relatable, um, if what kind of kinetic energy does a baseball have? Well, how much work did you have to do to throw it? If you did 6 joules of work to throw it, it's going to have 6 joules of kinetic energy. And on the other end of the throw, there's a person who catches it. Whatever work you would have to do to stop it, that's how much kinetic energy it has. So if someone throws it with 6 joules, the other person on the other end will need negative 6 joules of work to stop it. Um, I'm not going to derive the kinetic energy equation, but since it's related to work, well, I'll just skip all this and just go right to the kinetic energy equation. It actually depends upon two things: the mass of the body. Obviously, more massive bodies would have more ability to do work when they were moving. A bowling ball at the same speed of a bowling ball would do much more work than a baseball at the same speed. But speed actually has a greater effect in kinetic energy because kinetic energy and mass have a direct relationship. So double the mass at the same speed, you're going to get double the kinetic energy, triple the mass, triple the kinetic energy. But kinetic energy and velocity have a direct square relationship. Direct square. So how does that work? So if a person is moving triple the velocity that they moved before, it's going to have 9 times the kinetic energy. And just to make it real, if you're watching a football game, it would be 9 times harder to tackle that same person if they were going 3 times faster. You'd have to do 9 times more work to tackle that person. So triple gives you 9. Anything you do to a squared variable. Double would be 4 times the kinetic energy. 4 times the velocity would be 16 times the kinetic energy. That's the direct square. The plot of kinetic energy and mass, being that it's direct, would look like this. And kinetic energy and velocity would have a different shape because that's a direct square. That would be an second order exponential plot. It'd be curved. The work done, again, this is that close relationship between work and energy. Work is done on an object, the kinetic energy is changed. It could be changed two ways. Well, what kind of work done on an object? When is the work done on an object negative? When the change in kinetic energy is negative. So if you, that's a KE, let me fix that. So when the change in KE is negative, you must be doing negative work. Work catching a baseball on the other end of a catch, the work would be negative because the direction of the force and the displacement would be exactly opposite, 180. To catch a baseball, the force it would be opposed to the displacement, direction of the displacement, so it'd be 180, and your work would be negative. And your change in kinetic energy would be negative. You would reduce the kinetic energy. When is work positive? When the work causes a change in kinetic energy that it's positive. So when you throw the baseball, you're increasing its kinetic energy, you're doing positive work. The force, the direction of the force, and the direction of displacement, well, they're in the same direction, so the angle between the two are 0 degrees. Everything related to work and energy is a scalar. So work's a scalar, power is a scalar, kinetic energy is a scalar, potential energy is a scalar, everything related to work or power and energy, it's all scalar. Let's try a problem. You've got a softball having a mass 0.25. It's pitched at this speed. By the time it reaches the plate, the other side, it slows down by 10%. Neglecting gravity, what's the average force of friction that cause that change of energy, that loss of 10% of its speed, if the distance to the plate is 15 meters. So, why did it even change? The work done by friction, of course, it's a negative work, is going to be equal to the change in kinetic energy, which we already know is negative because it's going from a fast speed to a slow speed. So this is going to be negative and this is going to be negative, which makes sense. So it equals 1 half mvf squared minus vi squared. And that will equal the work done by friction, which will be the friction force multiplied by the distance. And of course, that's going to be a negative friction force. So first of all, we've got a problem here. We've got kilometers per hour. We can fix that. And then we've got to deal with this whole slows by 10%. Watch this. Do a little factor label. That's what they call it, kilometers per hour. So you make some ratio. We've got to get rid of the kilometers. That means I got to put it on the bottom and then it'll cancel out. 1,000 meters is a kilometer. All these ratios equal 1. Then I've got get rid of the hours, so the hours are on the bottom. I put the hours on the top, and that's 3,600 seconds. 1 hour is 3,600 seconds. And when you work all that out, I actually have it over here. If you do it right, you get 26.39 meters per second, and we're not going to go significant digits to the end. So that's the initial velocity. Now, what is the final velocity? Well, if it slows down by 10%, then it's 90% of what it used to be. So the final velocity, again, if it slowed down by 10%, well, it's 90% of what it used to be. So it's 0.9 times 26.39. And we can find the velocity on the other end. Let me get out the calculator. So we do 0.9 times 26.39, and we'll find the final velocity because that's how we're going to be able to get VF squared minus VI squared. So 26.39 times 0.9 equals 23.751 meters per second is your final velocity. And now we've got to get back to our equation that the work done against friction, which is friction times D, equals 1 half, the change in the MV, change in the kinetic energy rather. So that's Vf squared minus Vi squared, and that all equals now, let's go over what do we have to find? The average force, which is the force of friction. So friction we don't know, but we do know the distance between the thrower and the plate, which is 15 meters. And so let's do a little substitution. 1 half m is 0.25 kg. That's 1 FM times Vf squared, so that is 23.751 squared, that's meters per second, minus the initial, which is 26.39 meters per second, and that's squared as well. That all equals the friction, which we want to find, times 15 meters. And if you do it right, now this is going to be a negative number, so good. Our friction will be negative, which we expect it to be because it's so our friction is negative because our change in the Vf squared minus Vi squared, that's going to be negative, and that'll give us this whole left side will be negative, and then we divide both sides by 15 to get solve for the friction. And with two significant digits, you get negative 1.1 newtons. So what's the concept here again? The the when work is done on my system, it changes the energy of my system. The only energy change I see in my example is that it changed kinetic energy because it changed speed. So the work done against friction equals the change in kinetic energy. This is something we'll really develop a lot more later on. But whenever work is done in the system, it changes the kinetic energy. Now friction is going to do negative work, so we're not surprised that this change in kinetic energy, which is 1 half mvf squared minus vi squared, All of that is the friction times the D. We know this D. Go down over here. So it's 1/2 the M that now that M is not 25, but 0.25. Let's stick that in there. Times the two velocities, times the quantity, the two velocities squared, because the equation for kinetic energy is 1/2 mv squared equals the work done by friction. There's that little F that we don't know. D is the 15. The work is F times D. And so we get a negative friction. Okay, let's leave this. Now, baseball, traveling a baseball with this mass, we're going to change that to 0.140 kg because grams is not a standard unit. It's going at this speed and it's caught by a glove which moves backwards. We're going to change that to 0.25 meters to give it a standard unit. What is the average force? Well, what's the concept? Now the glove does work on the ball to stop it. It, of course, with no surprise, it's going to be negative work. The work of the glove will do what? What will the work of glove? Will it change the kinetic energy of the ball? So what is the average force of the ball in the glove? Okay, force of the glove, call it F, well, let's not call it F sub G, that's confusing. So the force of the glove times the distance the glove moved, that's the work of the glove, will equal the change in kinetic energy. So what's that? That is 1/2 m. Now the final velocity is 0 because it stops the ball, but the initial was 32 meters per second. That's squared because it's 1/2 mv squared. So, okay, the force of the glove is what we don't know. We know that it moves back to 0.25 meters. That's what the glove actually does move back, and we know that. And that's it. That the glove is doing work when it moves back. It's doing that negative work. It's applying its force in the opposite direction of the displacement. We're told it moves back 0.25. So 1/2. Now the mass of the baseball is 0.150. When we turned it into kilograms, and we just do the math here. This is 0 minus 32 meters per second squared. And so we have a math problem now. I would square this, multiply by this, multiply by this, and then divide it by 0.25. And let me scroll up and see what we get. We get the force of well, I actually have this. So we get F times 0.25 meters. And the change in kinetic energy on the right turns out to be negative 72 joules. Divide both sides by 0.25 and you find the force equals that value when you bring it down to two significant digits. Okay, so what's the concept here? I had a ball whose speed changed, and when you do work, why did its speed change? Because negative work was done on it. Its speed decreased. So how much work did the glove do? The work that the glove do is always equal to the change in energy. Now, in this case, it's only kinetic energy. But whenever work is done on my system, it changes the energy of my system by whatever work is done. So the work done in the glove is going to be exactly equal to the energy change in my system. Kinetic energy is 1/2 mv squared. So there it is. Let's see. Now, power. I think I'm going to stop the video here and make a second power video.